I've now talked about one of the absolute highlights of additive combinatorics, namely Feynman's theorem. And I'm going to move on to another one, which is Szemerédi's theorem, which concerns when you can find arithmetic progressions inside a set. We're not going to prove Szemerédi's theorem in full in this course. That would be a bit too ambitious. But we will prove an important special case of it, which gives some indication of how to do it. And then actually later on in the course we'll prove a more advanced special case, but we'll prove it for subsets of fp to the n. I'll say what the theorem is in a moment, but subsets of fp to the n, where the arguments are cleaner, but the ideas are sort of essentially the same. So what does Szemerédi's theorem say? Well, perhaps I'll start actually with a theorem that you may very well know already, but in fact you may well have been to lectures where it's been proved, and that's van der Waerden's theorem. And you may well have heard of Szemerédi's theorem as well, of course. So van der Waerden's theorem. And that says that if you colour the integers from 1 to n with r colours, so I should say for all r and k there exists an n, such that if you colour the integers from 1 to n with r colours, then some ci contains an arithmetic progression, which I will always abbreviate by AP, of length k. I should say, by the way, that for me the length of an arithmetic progression is not the diameter. It's if you've got an arithmetic progression a plus d up to a plus k minus 1d, I'll say that the length of this arithmetic progression is d, because it's got d elements. So the length is just a cardinality. And the number d here I'll call the common difference of the arithmetic progression. I won't write that down because that's reasonably standard terminology, but I just want, occasionally people have been a bit confused when I've said length and thought I meant something like this minus this. Okay, now Szemerédi's theorem is a rather far-reaching generalization. And it says the following. For all delta greater than 0 and for all k, there exists an n such that if A is a subset of 1 to n and has density at least delta, then A contains an AP of length k. Now, when I say it's a far-reaching generalization, what I really mean is we're strengthening. And let's just see why. So let's see why Szemerédi's theorem trivially implies van der Waerden's theorem. The reason is we set delta to be 1 over r. Then we choose our colouring of the numbers from 1 to n by the pigeonhole principle. At least one of these sets has density at least delta if we've chosen delta to be 1 over r. And so that colour class, the densest colour class, or indeed any colour class that has density at least delta, or at least 1 over r, if we've chosen Rn appropriately, will contain an arithmetic progression of length k by Szemerédi's theorem. So what that rules out, if you follow through van der Waerden's theorem, it may be that the colour class you pick out is a rather sparse one or something, but Szemerédi's theorem says that, in fact, any colour class that's not tiny, as long as n is large, any colour class that contains a positive proportion, provided n is sufficiently large, must contain a progression of length k. Now that's a really quite simple-looking statement, and given that, it would be quite natural to think that well, one of two things could happen. Either it would be false, or it would be true with a reasonably straightforward proof. But what makes it interesting is that neither of those is the case. It's true, and it doesn't seem to have a reasonably straightforward proof. And in fact, there are some arguments one can give that sort of suggest quite strongly that there shouldn't be a too simple proof. Now, what we're going to talk about in the next part of this course is, first of all, Roth's theorem, and that's the case k equals 3 of Szemerédi's theorem, which was proved before. So Roth proved his theorem in about 1952 or 3, and Szemerédi found another proof of Roth's theorem in about 1969. I may have got these dates slightly wrong, and then proved the case k equals 4 in, I think, 1974, and then the full theorem in 1975. It was something like that. It was a rough chronology. And since then, there have been various other proofs of the theorem, and all sorts of extensions have been proved as well. So one of the reasons I want to do Roth's theorem is it's a really good, a bit like Fermat's, it's a really good example of how Fourier analysis and combinatorial arguments can mix to give really quite non-trivial results. And so the first thing I want to do is explain how Fourier analysis comes into this. So what we're going to show, roughly speaking, is that if A is a set and it's going to be a subset of Zn, where for convenience n will be odd, and if, so I'm going to say this very, very vaguely, and then I'll give a more precise statement. So if A is a subset of Zn, a dense subset, and if all its Fourier coefficients, perhaps I don't need to put the modulus because I'm just going to say it is small for all r not equal to 0. So all non-trivial coefficients apart from the one that's guaranteed to be 0 because it's guaranteed to be reasonably large because it's the density of A. And we'll see what small needs to be in a moment. Then A contains plenty of, I'm going to abbreviate arithmetic progressions of length 3 by 3 APs. And the full proof that we're going to give of Roth's theorem, which I will state more formally when we get to it. So I'll prove some lemmas that we'll use, and then I'll state the theorem. The proof is going to split into two cases, and one case will be that if this holds, this hypothesis holds, then we get plenty of arithmetic progressions of length 3. So that does one situation, and then in the other situation there will exist some r such that A hat r, some non-zero r such that A hat r is not small, and then we will use that information to, well, what we'll do is we'll find a long arithmetic progression inside which A is a little bit denser. And then we'll iterate that argument. That slightly denser set, we will then, it's a little bit complicated because that will live inside a progression and not inside a cyclic group. And that's actually a little technicality that we're going to deal with quite soon. But I think it's now a good moment actually just to state the first lemma that we'll prove. So it's a little bit more general than it's not completely obvious that we need this generality, but it's actually very useful. So let A, B, and C be subsets of Zn, where n is odd, with densities alpha, beta, and gamma, obviously respectively, but I might as well write that. And we're going to suppose that n is greater than, or is greater than, I think I want 2 over alpha, beta, gamma. As usual, I reserve the right to change these sorts of things, and they're not very important. Then either there exist x and a non-zero d such that x plus d, x plus 2d, so we've got a nice little progression of length 3, belongs to A cross B cross C. So in other words, we've got an arithmetic progression of length 3 with the first element in A, the second element in B, and the third element in C. So this is why I mean it's a slightly more general setup. And by the way, if you've got 3 dense sets A, B, and C, you can quite easily come up with examples where this does not happen. There'll be, say A and B were a little interval over here, and C was an interval over here. You wouldn't be able to find an arithmetic progression of length 3 with the first 2 things in there and the third one in there. But with the extra hypothesis that we're about to impose, it turns out that you can. Or there exists r not equal to 0. So here's our not small Fourier coefficient. A hat r is greater than or equal to alpha beta to the half gamma to the half over 2. And that number will arise fairly naturally. Okay, now we can think of it another way. We can say if all the Fourier coefficients are smaller than alpha beta to the half gamma to the half over 2, then that we must be able to find some x and d such that this is the case. Now, that's a slightly misleading way of putting it, because we're not actually going to try to find x and d at all. What we're going to do is something much more, well, something that often happens in combinatorics. Instead of trying to find things, you count them and show that the number is non-zero. So we're going to just write down an expression for the number of such triples. Actually, it'll be normalized, so it'll be an average rather than a sum, but anyway. And then we'll notice that that expression can be manipulated into a form where it involves convolutions and inner products and things like that, and so Fourier analysis comes naturally into play. So we'll bring the Fourier analysis into play, do a very simple argument, and deduce the lemma. So that's the rough idea. So let's go. So let's say consider the quantity, which I'll think of as the arithmetic progression density inside A cross B cross C. So it'll be the average over all x and d of AX. Remember, that's short for 1a characteristic function associated with A of x. That is equal to AX. AX B x plus d C x plus 2d. So this is not, if I put a sum there, that would be counting the number of progressions of length 3 in A cross B cross C. If I put the average there, then we can think of it actually in a very intuitive way. It is the probability, if you choose a random x and d, that x belongs to A, x plus d belongs to B, and x plus 2d belongs to C. So it's proportional to the number of such things. In fact, it's n to the minus 2 times the number of progressions of length 3. So if this quantity is non-zero, not if this quantity is non-zero, because I didn't say we want d not to be 0, but there are not going to be very many of these things when d does equal 0. We'll come to that later on. Now, there's another nice way to write that, which is, perhaps I'll put it here, it's the average over all triples x, y, z such that x plus z equals 2y. So y is the average of x plus z. So this is y, that's x, and that's z. AX. I'm going to put a CZ here, BY, just because it's convenient to have it that way around. And I'm going to do this very, very, very carefully. So I could jump lots of steps or sort of do 2 or 3 steps at once, but I'm going to put in all the steps. That's the average over all u of the average x plus z equals u ax cz. And I don't really need these, but it'd be sort of clearer if I put some brackets around there. And then I have b of u over 2, because 2y equals u, and so y is u over 2. And this thing here is just a star c of z, so we have average over u of a star c evaluated at u. That's just the definition of convolution. And this b of u over 2, if you go back to when I stated and proved the dilation rule, I called that b2 of u. So b2 stands for dilation in that sense. And now we're going to start using Fourier analysis. We've got convolutions, we've got dilations, we've got an inner product. And so, well, let's do the inner product first. Actually, so I haven't done any Fourier analysis. I'm going to just write it more explicitly as an inner product, first of all. And now let's apply Parseval first of all. So that tells us that the inner product of those things is the same as the inner product of their Fourier transforms. Next, let's use various rules. So we've got the convolution law that tells us how to take the convolution, how to take the Fourier transform of a convolution. We just take the product, a hat, c hat. And the Fourier transform of our dilation is the sort of inverse dilation of the Fourier transform. So that's b hat, I'll put a bracket around just to be absolutely clear, 2 to the minus 1. So by 2 to the minus 1 I mean the inverse of 2 mod n. So you could call it n plus 1 over, what is it? Yeah, n plus 1 over 2. And that equals, let's just write out explicitly what that thing is. It's the sum over all r of a hat r, c hat r, and then b hat of 2r bar. That's just using the definition of the inner product, the definition of the dilate by 2 to the minus 1, and I don't know, definition of a pointwise product, I suppose, and the definition of the inner product on the Fourier side. I've used various things there. And that equals, by the fact that b is a real valued function, so this is not an important step what I'm about to do. I could just not do it, but I somehow prefer to write it like this. But as I say, if I kept it like that, it would make no difference. And I'm going to do one last thing, which is perhaps a slightly less obvious step, but I'm doing it with the proof that I'm about to do in mind. So I'm going to split this up into 2 terms. One is the term where r equals 0, and the other is the term where r doesn't equal 0. So when r equals 0, we get a hat 0, c hat 0, b hat of 0. And if you remember, a hat of 0 is just the density of a, and similarly with b hat of 0, c hat of 0. So we get alpha, beta, gamma here, plus the sum r not equal to 0 of a hat r, c hat r, b hat of minus 2r. And what are we trying to do? We're trying to prove that this quantity is not too small. And we're actually going to show that it's at least alpha, beta, gamma over 2 under suitable unsuitable conditions. I think this has been a rather long page, so I deserve a fresh one. So we'll leave that term where it is, but just before we go any further, I just want to make a comment about this term here, which is rather important. So let's just go back and imagine that we've chosen the sets A, B, and C completely randomly. So I've chosen elements of A with probability alpha, and I've chosen them independently, and elements of B with probability beta, elements of C with probability gamma. okay, they won't necessarily have size exactly alpha n, beta n, gamma n, but they'll have size with high probability size very close to that. So it's not a bad model, so to speak. So in that case, if I take a triple x, x plus d, and x plus 2d, the probability that x lies in A, x plus d lies in B, and x plus 2d lies in C is exactly alpha, beta, gamma. So the average of this quantity here, or the expectation of this average, will be precisely alpha, beta, gamma. So this alpha, beta, gamma is saying this is sort of what we expect to get. If we just took 3 random sets, we'd get alpha, beta, gamma, n squared progressions of length 3 in A cross B cross C, approximately, with high probability. So that's the sort of random bit, and this is telling us, this part of the thing is saying to what extent we depart from randomness. So it's telling us this is measuring somehow the departure from randomness. And what we'd like to prove is that this part is not big enough to cancel out this part here. So let's now estimate this thing, and this is where I said we did some Fourier analysis, and then we have a simplish argument. So let's rewrite it. So it's sigma a hat r, but I'll put a modulus sign around it. That is less than or equal to, now the maximum such that r doesn't equal 0 of a hat of r times the sum of all the rest. So the sum, and actually I'm going to add in the 0 terms again. Yeah, you've seen this, some trick a bit like this before. So b hat of minus 2r, I'm putting these back in their sort of natural order, alphabetical order. Let's put some mod signs around those. And now I'll apply Cauchy-Schwarz to this sum here. So that's less than or equal to the max r not equal to 0. And the reason I'm applying Cauchy-Schwarz is that that's going to turn things from, it's going to turn this inner product into something to do with L2 norms. And we know all about L2 norms because we have Parseval. Maybe I'll write it in full. Sum r b hat minus 2r squared to the half sum r c hat r squared to the half, and that equals, again, this first term here, the largest non-zero Fourier coefficient, and then this thing is just the L2 norm of b, and this thing is of b hat, I mean, and this thing here is just the L2 norm of c hat. Now, why is this the L2 norm of b hat? It's because as r runs through all of Zn, so does minus 2r, and there I've used the fact that n was odd. That's the main place where that's used. And we know, this was another remark that I made in the basic properties of the Fourier transform, that the L2 norm of b hat squared is just the density of b, so it's beta, and this thing squared is gamma. So we get beta to the half, gamma to the half, max r not equal to 0, a hat r. So we conclude that if sum r not equal to 0, a hat r, c hat r, b hat of minus 2r is greater than or equal to alpha beta gamma over 2. Remember that, so if it cancels out even half of this alpha beta gamma term, then the max r not equal to 0, a hat r, is greater than or equal to alpha beta to the half gamma to the half over 2, which was the conclusion that we wanted up here. Now where does this n greater than 2 over alpha beta gamma come? So if that's not the case, then we'll have that the average of ax bx plus d cx plus 2d is greater than 1 over n, then there exist x and d not equal to 0, such that x plus 2d, x plus d, I mean, x plus 2d belongs to A cross B cross C. Because the number of degenerate progressions of length 3, by which I mean of the form xxx, is n. And when we divide by n squared because we're averaging, then that means that we get down to 1 over n squared. So the contribution from degenerate progressions of length 3 is at most 1 over n. So as long as you're bigger than 1 over n, there must be some non-degenerate ones. So a sufficient condition, since we've just got that it's that if that's not the case, then we have that this quantity here is at least alpha beta gamma over 2. So a sufficient condition is alpha beta gamma over 2 is greater than 1 over n, or n is greater than 2 over alpha beta gamma, which I hope is what I wrote up here. It is n greater than 2 over alpha beta gamma. So we just need that condition just to make sure that the progressions that we find are non-degenerate ones, non-trivial ones. I could do slightly better actually, because the number of degenerate ones that could be in here is actually at most the maximum of alpha n, beta n, and gamma n, because they've got to belong to all of A, B, and C. In fact, it's almost the minimum of alpha, beta, gamma actually. So, but that doesn't really, I don't care about that improvement. Okay, so that's one lemma, which will be very important. Now, as I said before, what we've got to do is a two-stage argument. So we've now got to think about what happens if you do have a large Fourier coefficient. So we've proved Roth's theorem, but with a massive extra hypothesis that A only has small non-trivial Fourier coefficients, which is a sort of quasi-randomness hypothesis, sort of saying that A behaves a bit like a random set in an important sense. This idea of quasi-randomness is a very big theme in additive combinatorics, and also in parts of extremal graph theory actually, and extremal combinatorics more generally. So we're now going to prove another lemma that is going to be very useful for the purposes of getting some kind of information in the case where you do have a large Fourier coefficient. I'm not going to relate it directly to that straight away. I'm just going to prove a rather general lemma. So I don't think I need any definitions for this. So let's perhaps this isn't really important. I could have said it in a lemma, but maybe I'll just say in advance. I'm going to talk about if I've got a set of complex numbers, then the diameter of x is just what you think it is. So it's the sup of z1 minus z2, such that z1 and z2 belong to x. And in fact, we're only going to be talking about finite sets, so the sup will be a maximum. Right, let's go. Lemma. Let theta be a real number. And let n be some integer, positive integer. Then set 1 up to n can be partitioned into arithmetic progressions P1 up to Pm, of size at least, so I want to say then for all epsilon greater than 0, so of size at least epsilon n, and I've unfortunately forgotten, I think I get 32 pi, and I definitely have to reserve the right to modify that. If it comes out differently this time, I prove it. Such that the diameter of E of theta pi is less than or equal to epsilon for each I. So what I mean by this, just to be absolutely clear about it, so pi is some arithmetic progression living inside 1 up to n. Theta pi, I just multiply everything in that arithmetic progression by the real number theta, and I get some arithmetic progression of real numbers. Then I apply the e of that, so that, remember, recall that e of something, e of alpha, is just e to the 2 pi I alpha. So this map E wraps the interval 0, 1 round the unit circle, and the interval 0, 1, 2 again round the unit circle, and so on and so forth. So I take my arithmetic progression, I stretch it a bit, and I wrap it round the circle in a nice way, and then the diameter of that will be less than or equal to epsilon, because somehow these progressions are chosen in such a way that when you do this multiplication by theta and wrapping, you get something that's not too big. And the proof of this will be similar to arguments you've seen before, I think. And it uses, the basic idea is just hit it with the pigeonhole principle. Unfortunately, there's some annoying technical bits towards the end where you get involved with integer parts. I could just ignore those. In fact, maybe in this video I will be rather cavalier about those integer parts. But in the notes, I've been a bit more careful. I think that's actually good, because I don't want to get too hung up on, I just want to sort of confuse you with those unimportant details. I'd rather just give the idea of the proof, and then obviously you do want to see the details at some point, so there you can look at the notes. So how do we prove it? So let m, not m, what should I go for, t, be a positive integer to be chosen later. So we'll do some optimization towards the end. Then by the pigeonhole principle, of the numbers E of 0, E of theta, all the way up to E of t theta, we can find two E of u theta and E of v theta, two different ones obviously. Let's just say with u less than v, such that now the circumference of the unit circle is 2 pi. So we can get that their distance, the arc length between them will be at most, and hence their Euclidean distance is less than or equal to 2 pi over t. So now I'm going to let d be v minus u. Then for any S, we have E of theta, well, I'll put it the other way around for consistency, S d theta minus 1, I'll put it the other way around, 1 minus E S d theta, it's the same thing of course, is by the triangle inequality less than or equal to 1 minus E of d theta plus E of d theta minus E of 2d theta plus dot 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 plus E of s minus 1 d theta minus E of s d theta. But this thing is got from this one just by multiplying that by E d theta and that one by E of d theta. So I've multiplied this whole thing by E of d theta, which has modulus 1. So this modulus is equal to this modulus. In fact, they're all equal to each other. So that just equals S 1 minus E of d theta, which, oh, I didn't comment, sorry. But then 1 minus E of d theta is equal to this thing here, so that's also less than or equal to 2 pi over t. To achieve that, I multiplied this by e to the E of minus u theta, and this one by E of minus u theta as well. So that's less than or equal to 2 pi s over t. So what can we say? So provided that s is less than or equal to, so we want this to be at most epsilon, so provided that's at most epsilon t over 2 pi, we get that a progression, or we get that if p is a progression of common difference d and length at most epsilon t over 2 pi, then the diameter of E of theta p is less than or equal to epsilon. So we'll be fine as long as we can partition the numbers from 1 to n into progressions of common difference d and length at most epsilon t over 2 pi. So it's rather obvious how we do that. We just take the numbers 1 to n, or obviously how we're going to try to do it anyway. And we first of all partition into residue classes mod d. So we'll have 1 d plus 1, 2d plus 1, and so on, and then 2d plus 2, so d plus 2, 2d plus 2, etc. So we do that, and then each residue class we will then just partition into chunks of size at most epsilon t over 2 pi, at least that's the plan. And we'd like those chunks to be reasonably big. So let's just get rid of all that. I didn't really need that, I just was writing it down so I could write something as I was talking. So partition, this isn't the full partition we're aiming for, but partition 1 to n into residue classes mod d. And then we would like to partition each residue class into sets of size about epsilon t over 2 pi. So when can we do that? Well, what we can say, that one problem is that the residue class won't necessarily have size that's a multiple of epsilon t over 2 pi. But what we can say is if the residue classes aren't too small, so if they have size greater than, or so let's say at least epsilon t over 2 pi, then we can partition them into sort of intervals. So by interval, I don't really mean literally an interval, but I mean a sort of sub-progression of common difference d. So let's put that in inverted commas, just in sort of size between epsilon t over 4 pi and epsilon t over 2 pi. Now here I'm starting not to be very careful about integer parts, so if these numbers are very small then that may not be quite 100% true. But as I say, I was a bit more careful in the notes. So that we'll be quite happy about, but the residue classes have size at least, well, it'll be something like the floor of n over t. So we need, so let's just ignore that floor. So basically we need, for this whole thing to work, n over t to be greater than or equal to epsilon t over 2 pi. So that says t is less than or equal to, I've changed my little n into a big N. Let's change it back to a little n. It's t is less than or equal to 2 pi n over epsilon square rooted, and then that will give us intervals of size between epsilon t over 4 pi. So this gives us each pi has size at least epsilon t over 4 pi which is yeah, so I sort of assume I can take t actually equal to this, which again is not necessarily true because of integer parts and that kind of thing. So sort of roughly, so that epsilon becomes an epsilon squared if I put it inside the brackets, so I get it, and the pi becomes a pi squared and so on. So I get epsilon over pi, and that 4 is a 16, so that's over 8 n to the half. Now I actually got 32, and that was because of a couple of moments where the integer parts, I had to be a little bit fussier about integer parts, and that gave me an extra factor of 2 outside the whole thing, which multiplied this number here by 4 and got to me to a 32. So that symbol there is not to be taken at all seriously. It just means that sort of idea. And as I say, if you do the argument a bit more carefully, then I think I'm pretty confident that at least if n is not tiny, then you can get it with 32. And I think if you're more careful, you can do it a bit better than that as well. Now, the reason I don't really care about all this is that in applications, I don't actually care even slightly about what this constant is, or at least for Roth's theorem, I don't care at all about what this constant is. I don't even really care what the dependence on epsilon is, it'll turn out. I just care, in fact, I don't even care that this is the square root. If it was a sort of fourth root, that would be just as good for our purposes. So this bound is not terribly important for the purposes of proving Roth's theorem. And of course, it's always nice if you've got an argument like this to think about what the best bound is that you can get. So I've made a bit of an effort. But if I'd been a little bit less careful, I might not have got epsilon to the half. I might have got epsilon or something like that. I think I've slightly, this video has become reasonably long, so I shall stop at this point. And in the next video, we'll see how to use this lemma in order to get from having a large Fourier coefficient to getting A to be denser inside an arithmetic progression. And once we've got that, we will be pretty much there. So it'll just be a question of putting everything together, doing a bit of back of envelope calculating, and we'll have a proof of Roth's theorem. So I hope that I'll be able to finish off the proof of the whole theorem in a reasonably short video. So I will stop at that point.